Again, hello everyone. Now, this is the last week of our laboratory sessions, but we will have an additional week next week concerning the final exam. We'll try to solve questions for the final exam so that you review your knowledge, since we've covered the frequency domain. And now we will today cover the state space approach. Therefore, we'll have a final session where we repeat everything and try to help you out in the final exam, hopefully. Now, last week we had, or last session at least, we had the frequency methods. We've discussed them, and we've looked at the p-type controller, the time delay part, and also, as far as I remember, we've also designed a lag controller. And now there was also a lead controller, but that will be covered in the next week's session. Now this week, we'll change our system model. We've used the transfer function model, which is acquired in the Laplace domain up to this point. But starting from, or in this session, we'll see how we can do this differently. We are going to have a state space model. Now, as you might already know, we don't have a transfer function. We don't have the Laplace domain available here. Therefore, in order to judge a system based on its stability or on its behavior, we need to know what the state space model gives us in terms of tools. And we also have to be able to analyze such systems. And at the end of the day, we'll also try to synthesize a controller for that. And we'll hopefully try to explain what the pros are and cons are. So, yeah, enough of that. Let's see. We have basically, let me zoom this a little bit. We have basically four matrices that concerns us if we have a state space model. One of them is called A, and then, as you can see, it's not really that original. It goes on like B, C, and D. Now, this A matrix here is fairly important, and we'll see how we transition from a state space model to the transfer function or vice versa. So that's really the key point here. So let me start with a discussion about the transfer function that we've, for example, covered so far. Let me give you an example system. Let's have that. Let's say we have such a transfer function. Now, this transfer function is between an input and an output. So therefore, we always write y divided by u. If we apply a certain input u, we'll get y. Now, this is an input-output relation. Now, if we have a certain system, this is what we look at. And using a transfer function is basically a classical approach. We call it that because state space is a more modern approach. We'll see why. Now, in terms of input-output, GS gives us poles and zeros, and then we already know how to interpret them in order to get some idea on the behavior of the system. But this is not the only way, and we'll see how we can transition or look at things differently. Now, let me pull out this equation here. Let's say that this is the relation that we look at. Now, as you might already know, the reason why we use the Laplace domain is because it has some advantages. We're not really able to look at a differential equation and then try to gain information about its behavior. But it is possible using the Laplace domain transfer function. But let's go back to the basics. Let's get the differential equation. So that would be the equation that we would look at. Of course, I can also write it down like the following: s squared times y. Let's have a multiplication here. Plus s 4s times y. And then plus 5 times y equals u. Now, transfer functions don't really have initial conditions. They are 0. If we acquire a certain transfer function, we take the initial conditions 0. So therefore, I can safely assume that s squared means multiplying with s gives us the derivative. Therefore, this is the second derivative of y. Plus 4 times, since I have 1s, I'll get 4 times the derivative of y. And then 5 times y, because this doesn't really change, and u, because it's a static relation. Now you can see I've obtained the differential equation of the system. But again, this differential equation does not really help us out here. But the state space model uses this differential equation and transforms it into a much simpler but bigger form. So by that, I mean that since we have double derivatives or third order, fourth order, or nth order derivatives, it's not really easy to even calculate the integral if we want to pull it out. Now, in order to prevent that, what we can do is we can introduce new variables. For example, I know that I can work with y. So let me call this x1, let's say, because I will introduce multiple of them. And the problem, the origin of the problem is that I have too many derivatives here. If I would have had such a differential equation, let's say y plus y equals, let's say 1, you can safely calculate y derivative by taking this, or let's even get rid of this 1. Let's look at the unforced differential equation here. Now, if I have this, I can just take this, look at this, and then since this is dy divided by dt equals minus y, what I can do is I can state the following: dy divided by y is dt. Taking the integral gives me ln y, and or natural log y is equal to t plus c, maybe the since this is an indefinite integral. Now you can see that directly we had a minus sign here. So minus t, then this would be e to the power of minus t plus c. This is still up there. And I can just convert it into, let's say, another c, capital C maybe, times this. So you can directly see that this is the equation, this is the solution, and I've obtained the solution. I can work with first order derivatives. And therefore, what we'll try to do using a state space model is to just reduce the second order differential equation into 2 first order differential equations, because I cannot neglect the second order derivative here. But what I can do is I can just introduce 2 first order equations in order to model the system. And that's exactly what I'm going to do. Now, in order to do that, we can start with defining y as a unknown parameter, and then look at the derivative. x1 derivative is equal to y derivative. But I don't want to have this first order derivative because there is another derivative here, y double prime. So therefore, I'll introduce a new unknown here, no new variable, x2. If I take the derivative of that, that will be equal to y double derivative. And at this point, I can stop because I had a second order differential equation, which means that I need 2 first order differential equations. This would be one of them, and then this would be another one. So these 2 should be sufficient in order to model the system. And let's see, I'm basically getting rid of the y here because my new variables are x1 and x2, or the so-called state space variables. And then we have this one here, but this has already its relation, so I need this equation here. So what I'm going to do is I'm going to use this equation in line 16 and plug in all the new variables. For example, I have y double dot. So let me take this and plug it in here. This is basically x2 on its own because it's y derivative. You can look it up here. You can maybe write down x1 derivative, but that doesn't make any progress, so therefore I'm choosing x2. And y was equal to x1, so therefore this would be then the second equation. So this is basically the first equation here, this one, and this is the second equation. So let me get rid of this one here. So there we go. This is basically our model. But in order to tidy up stuff, I have to define it like that. So let me pull this one to the right. So there we go. Using these two differential equations, first order differential equations, I'm modeling the same system. Of course, a question might be the following. Why would I do that? Why would I just reduce the order here and increase the number of equations? Well, because using a matrix notation, I can get a general solution of the differential equation set here. And let's put this into a matrix form. Now, in order to put this in a matrix form, I'm going to define a vector here. So x1 and x2. So this is a column vector. And therefore, if I'm looking at x dot, it would be the individual derivatives here. So that's also out of the way. Now we have x1 dot. So if I'm looking at x dot equals a times x plus bu, this would be the generalization because, well, you can see you have u, it's in the second equation, but it might also be as well in both of them. So a generalization is given here. So B is a vector and A should be a matrix because here we have the size 2 by 1. So this is a 2 by 1 vector. This is also a 2 by 1 vector. So therefore, if I have a little bit linear algebra, I can see that in order to have this, in order to be able to add them, they should be 2 by 1. So U is basically just one input. We are working with single input, single output systems. So U and Y are scalars. So therefore, B should be a vector of 2 by 1. And since X is 2 by 1, and the result should also be 2 by 1, if I'm pre-multiplying it with something, at least it should end with 2. So that's there. But also, the result would be then, let's say, m by 2 times 2 by 1. That would be m by 1, therefore 2 by 1. So it means that I should have a 2 by 1, 2 by 2 square matrix for A. So what is A and B? It's not really that hard. Let's see. So we will work row by row. So therefore, we'll see that. Let me just leave it there maybe. So for the first equation, the effect of x1 is not there. So it doesn't really affect that. So it's 0 times x1. And x2 has a coefficient of 1, therefore 1. Now let me also define this one here, b. So for the first equation, there is no u, so that will be 0. And let's look at the second equation. Here we have minus 5 times x1 and minus 4 times x2, which gives us the row because that's the way we multiply a matrix with a vector. So minus 5 and minus 4. There we go. And the coefficient here is basically 1. There you go. Now we have x dot equals ax plus bu. And that's basically it. But we've lost y because our relation is an input-output relation. We have a certain u here, but we don't have y. So we can solve that by including this one here. Maybe y is equal to x1 is a better statement. And if we want to stick with x, the matrix notation here, what we can do is we can assume that there is 0 times x2 plus 0 times u, because that would be the most general form. X2. There we go. So therefore, putting this in a again matrix form, let me just update that. This is just one row because eventually we'll get 1 by 1, a scalar, y. And here we have a 2 by 1 vector, x. So therefore, this would be 1, and then we will have 0. Since there's no u, we'll just plug in 0. So that's basically it. Now, we can see that we have, again, x, y, and u, and we're basically modeling the input and output, but we have additional data here. We have a variable x, which we can inspect and see what it really does. So now I've basically guided you through the conversion from transfer function into state space, but in a very specific example, of course. But this is the way that we will approach most of the time this conversion. What about the inverse? Let's say, since we have this already, let's say that we have a state space model. We have matrices A, B, C, and D. How can we convert this into a transfer function? That might be also important for some case. So here, the way is actually not really that, it should be very obvious, because the transfer function is, again, in the Laplace domain. We have a matrix structure here. What we can again do is we can just work with the matrix versions. Since we have x dot, instead of that, I could just introduce s times x equals, again, this here. Let me call it A and B, so it would be much easier here. So I've just plugged in x derivative, and instead of looking for, let's say, x1 derivative, x2 derivative, I can just multiply them with s, so individually. But of course, this is not really the notation that I should use in this case, because this is, I'm using matrices here, and this is basically a scalar version here. S is a scalar. Now, you can see that instead of doing that, what I can do is I can define it in the same format. I have x1 and x2 as a vector. This is the x vector. So if I want to get this result, what should I plug in here? This is a matrix, obviously, because this is 2 by 2 or 2 by 2 times 2 by 1. So I'm checking for the sizes if I struggle. And I can see that this should be a square matrix. What should be the content of this matrix? Well, I want to get Sx1. So S, 0 would do that. And 0, S would do the same for x2. So if you multiply s times x1 plus 0 times x2, you'll get sx1. And 0 times x1 plus s times x2 should give you sx2. So I've just generalized it. And this is obviously a very much familiar matrix, namely the identity. I can just pull this out. And there we go. We have S, I, and then X, basically. So I'm just going to plug in an identity matrix in here. So now I want to get a relation between X. Let me just capitalize this and get rid of the error here. I want to just work out the relation between U and X, because this is the dynamic part and this is the hard part. If I accomplish that, I can just use this static equation here in order to obtain the transfer function that I look for, because it should be between the input and the output. This is the input, but there's no output here. But I know that X is a special version of the output, or the output is a special version of X. I can construct that. So therefore, I'm going to take this, put it here. Now again, I can see that they have a common factor here. So that would be the factorization here. And then I can just use or look for the transfer function between X and U. That would be, now since I'm working with matrices, I should be careful with my modifications. For example, I want to calculate the relation between x and u. Therefore, I'm multiplying with the inverse of the matrix from the left. So I'm basically doing the same on the right-hand side. And this should give me an identity matrix. Therefore, I'll get rid of this part and I get x. If I divide it by u, I'll get basically what I want. And this would be then the result. Now, the relation between the input and the state space variables, or the vector here, is basically this. Now, note that Si matches the size of A. Therefore, if we have a 2x2 matrix in this case, we'll take the inverse of that. It's still 2x2. The size is still 2x2. And then we have a vector, B, which I've already stated that it is a 2x1 vector. So multiplying that with a 2x1 vector would give me again 2x1. So it seems like I can obtain this relation. I can work this out because sizes match and the steps are correct. Now, what about the static relation that I've talked about? Namely this one here. Let me call this C and then B. So here, I'm looking for the relation between y and u, so I can just directly divide by u. I'll get this. There we go. Now this is the same because u is scalar. If it's not 0, of course, you have to be able to divide. And, well, we have x and u, the relation between this. So let's just plug that in. Times nothing, basically. Well, I got rid of this part. Let me just put it there. So you can see that y and u, the relation between y and u, basically the transfer function, is stated as this one. So compute Si minus A, the inverse of that, pre-multiplied with C, post-multiplied with B, added to D. That's basically it. So if you take A, B, C, and D here, you should be able to calculate that. So let me just define A. There we go. And B. This is C. And D is equal to 0. So let me just define S, symbolic S. And the steps are fairly easy. I have to just use C times the inverse of S times the identity matrix 2, or 2x2, just 2 is the same, times B plus D. So maybe we should simplify it because we're using basically a symbolic toolbox and maybe pretty in order to have a pretty output. Let's see. Line 3. Oh, of course. It's not really defined. Now we've chosen 1, 4, 5 as the coefficients, and you can see we've obtained them back. And A was this, B was this, C, and D. Now, of course, here A is also in a special struct because we have a 0 here, and then this is basically the row that interests us. And for a 2x2 system, let me give you a quick note here. The sum here, the trace of this matrix, would give you the sum of the poles, because the eigenvalues of this matrix, basically, are the poles. So A is here important because we take the inverse. You can see that we take the inverse. And if you look up the inverse of a square matrix, you'll see that the determinant of this will pop up. So determinant of Si minus A is important to us. And let me show you why. So this should be familiar. S squared plus 4s plus 5. what did I calculate here? The determinant of Si minus A. Why? Because the inverse uses this, 1 divided by that, then times something else. So therefore, this is basically the denominator of the transfer function, or the characteristic polynomial of the system. So therefore, we've obtained s squared plus 4s plus 5. And we can directly see that we can solve the roots of this, 1, 4, and 5. And these are the roots. And note that the sum here is minus 4. And the trace of the matrix, you can just directly ask Matlab, the trace here, that's minus 4. And the determinant here is also important because that's 5. Why? Because the eigenvalues here, if you calculate the determinant of a certain square matrix, you're multiplying the eigenvalues. If you calculate the trace, you're summing up the eigenvalues. But for the 2 by 2 case, it's a special case where you can just directly see the relation between the two eigenvalues that are present here. So if you have the sum of, let's say, lambda 1 and lambda 2, or P1 and P2, and the multiplication of them, you can directly work it out. You don't really have to calculate a symbolic lambda and lambda I minus A, and then the eigenvalues and eigenvectors. That stuff is not necessary for the 2 by 2 case. So you can just directly look it up. Look for the determinant, that's the multiplication. Look for the trace, that's the sum. If you want to calculate the poles using the state space model here. Now, we've seen that we kind of look for the relation between, basically, if we are trying to obtain the state space model, we construct the differential equation, the corresponding differential equation, and then we just define new variables each time we take a derivative that's necessary, and we build the matrix form. If we want to use the state space model in order to obtain the transfer function, I've shown you that C times the inverse of Si minus A times B plus D gives you the corresponding transfer function. And it can be helpful for some cases. Now, enough with this discussion. Let's look at our today's task. We have a certain A, B, C, D value. What we can do is we can just use A, B, C, and D in order to obtain the transfer function. And that's exactly what we want to do here. So let's just get rid of this stuff here. Let's define A. That's 1 and 2, 1.4142, I guess. 282. 84. And then we have B, 2 and minus 1, and then C, 1 and 0, and D is 0. So you might ask yourself, why would I use the symbolic toolbox if I can define them using Matlab? So let's try that. Let's use the Matlab Ss function here. This Ss function is basically the equivalent of TF. If you're defining a transfer function, you give the numerator vector and the denominator vector. If you're defining a state space, you just use Ss and then provide A, B, C, and D. So if you're not sure, you can just go ahead and check it out by help or doc, and you'll see that it expects the matrices here, and the model is given here. So that's basically the model, and you will just provide the matrices here. So therefore, A, B, C, and D, that is basically my system. That is the way of defining a state space model in Matlab. And you can see it just gives you basically x1 dot equals 1x1 and 2x2, the sum of that. And x2 dot is equal to that times that, summed up. And you can see that the first equation has 2 times u in it and minus 1 times u for the second equation. And then you can also see what the output would look like in terms of x and u. Now, this is a nice representation, but we want to acquire the transfer function. And for that, there are multiple ways. One of them is to pass it like that. Since this is a system, MATLAB can convert it into a transfer function, but it might be a problem if it only works with the numerator and denominator. So let's check it out. Can I use it like that? I can. So that's good. Now, I've basically used a system model. I've passed it to TF and it converted it directly. So that's good. Now, well, this is the transfer function that I have. Now, what if I'm looking for a validation method? So I have a state space model and I have also a transfer function. They are supposed to be the same. But how can I check if it's really a valid transfer function, if they are the same system? Now, here I've talked about the fact that the eigenvalues of A are the poles. So what I can do is I can check for the eigenvalues of this and look if it's if the values are matching the poles of the transfer function representation here. So in order to do that, I can just use eigen, which is eigenvalue. And if I plug it in, I have 0 and 3.8284. And I can see it's basically almost 0, but we have some numerical issues here. But other than that, if I assume that this is 0, then I get one pole 0, and the other one would be 3.82 here. Now, let's check for the zeros and poles. And we have an interesting thing here. We see that this system has a 0 on its pole. So there's a pole 0 cancellation that we didn't get rid of, which is interesting because we have, if we cancel out the poles and zeros, we'll have a scalar system. If not, it looks like it's a singular system. So it's interesting. And this is a special case for that equation. Now, what happens if I use the symbolic toolbox here and use the formulation that I've already shown you? S times I, then minus A times B plus D. Let's simplify it. Now, it is really interesting to note that the symbolic toolbox gave me 2 divided by S, whereas MATLAB gave me 2S minus 7.657, etc. Of course, what we can do in order to get the same effect is the following. We can just look for min rail. And it kind of gets rid of the pole 0 cancellation, but we still have a certain value that's bothering us. So we have to give it a certain threshold, maybe, in order to resolve that problem. Still not working, as I can see. Yeah, we are not getting rid of that. So let me just check the documentation if there is something special that we can do. So mean real, the tolerance, and then there are some examples. Let's see. Well, yeah, that's basically it. We have a tolerance, but it's not really giving us 2 divided by S, but you can see it's almost that. Now, why can this be a problem? Or why is this a problem? Because we didn't get basically the same, even though we forced MATLAB to get rid of the pole 0 cancellation. So let me just take this back, maybe, and look at this. There's a difference. So we have that, which looks like a second-order transfer function, and we have this one, which is a pure integrator with a coefficient 2. So the reason for that is basically here, hidden here, because there's a special thing going on here. This is 1.4142, and if you remember, this is the square root of 2. And this is basically 2 times the square root of that. This is basically A. Now, if we try min_real again, see if it's making a difference. It does. Now we can see the numerical effect here. The approximation of the square root 2 and 2 times the approximation of square root 2 is not the same as writing down square root 2 into the matrix here. So numerical sensitivity is important because you're taking, at some point, you're taking an inverse and it's going to affect you. But here we have a polar cancellation. A slight error showed us that it could be transitioning from a second order transfer function into a first order one. Slight numerical differences can cause problems in this case. So therefore, let's stick with the previous version. Like that, because we can get rid of that. So there are 2 important aspects that we should cover here if we're talking about state space models. One of them is controllability, and the other one is observability. Now, well, what it roughly means is that if a system is controllable, then you can design a controller that changes the location of the poles. I can just summarize it to you like that. If it's a controllable system, you can move the poles as you wish. So that's important. Observability is basically also the same thing, but we will cover it in the observer design part. So, and the way of checking for controllability is also important because we'll use it later on. And it is fairly easy. What we do is we just use b and a times b, and then a squared times b, and then so on and so forth. So a to the power of n minus 1 times b. That's basically the formula that we are looking at. Because we have b here, we have n minus 1 here. So one of the columns is already b, but the next column, or how many columns more there are, is basically decided by n minus 1. So if we have a second order or a 2x2 system here, we just get rid of everything here and we have such a formulation, which is the controllability matrix. So matrix controllability, let's call it that. Or phi c would be also a valid definition here. So what is this basically? Because we have an interesting thing going on here. Now, I'm not going to go into much detail, but what we are looking at is basically if we have an effect on x dot using b times u, and then we take again another derivative here. X dot is basically it's basically a times x, so we have a relation between b and a. We have to calculate a times b in order to be able to just assign another pole, etc., etc. It's just too much detail. What you have to know is here to check out this matrix. If this matrix is singular, or if you cannot take the inverse of the system, then it's not controllable. So that's the issue that we should be aware of. So let's calculate this. And we can see that, okay, this was b already. That's not a problem. But if I multiply a and b, we get a 0 column here. And this is basically singular. If you calculate the determinant, you'll see that it's 0, and therefore you cannot take the inverse. So here we can see that 1 and 2. And here, if this is square root 2, this is 2 times square root 2. So there's basically a dimension that's not necessary in this case because it's the same equation. So that's the issue here. So we have basically the same equation here. So not too much detail here. And our output is just this one, and we have a system that's not really controllable. So if we have the eigenvalues here, it means that I can design a controller, but I cannot move one of the poles of these. I can just change one of them, and the other one will never change if it's not controllable. If the other pole if the pole that I cannot change is stable, then it's stabilizable, which is a weaker definition of controllability, but yeah. Now, we have seen that a 2x2 system, state space model, can be converted into a transfer function. If there's a pole zero cancellation, for example, then there might be the possibility that we might have a not controllable system. So in this case, this system is not controllable. So what I can do with this is basically, if we have this specific case here, I can just reduce this and get rid of the pole zero cancellation. I'll get just a first order equation in this case. I'll show that in a minute, but let me show you what the observability, which I've not really defined in this case, is. It is basically C times A to the power of n minus 1. Basically, again, a to the power of n minus 1 is the thing here. And let's run that. And let's look at the determinant of phi O, and it seems like it is an observable system. Now, it is important to note that the observability relies on the C matrix here. Controllability depends heavily on B and, of course, A, because A is the system matrix that's defining the behavior. It's responsible for the poles. B and C is basically the way that the input interacts with the system and the output that is generated by the system. So it's really important. D is basically a direct way from input to output. It's just a static way, a feed-forward path for that matter. So it's not really that much occurring in our problems. But if it's there, you have to know how to handle it. But most of the time, for most real systems, it's equal to 0. It should be a biproper system if we want to have a D value there. So enough of that. Let's check out our next task, basically. Now we have a special system. I'm going to show you from the PDF once I'm done with the other stuff here. But let's move on. Calculate the stability interval for a p-type controller and design a state feedback controller for the given state space representation. So we'll look for the stability of the system acquired in A, which is basically obvious because we have 2 divided by S. So it's really K positive is stable and K negative is unstable. And if we want to assign a certain pole, we have to choose half its value. For example, if I want to assign it to 4, then I have to choose 2, and that's sufficient. Why? Because we will have S plus 2 times K as the characteristic polynomial. And if K is 2, we will have S equals minus 4. So this is not really that exciting to analyze as a system, but what is exciting is that we have a new definition here, a new controller. That's called state feedback controller. So let me talk about the state feedback controller. Now, the name implies the structure of the system, this controller. It's called state feedback, and we call X the states of the system. So we have basically X dot equals, let me write it down here. We have basically X dot equals AX plus BU. And here X are the states. So if we are feeding back X, what we are doing is basically we are taking X1, X2, and we are using this as feedback. So that's nice. But how can we use or combine these two signals into a control signal? Because the controller produces the control signal. So what is the control signal here? Basically, it's U. Why? Because in the classic feedback or transfer function here, when we place a controller, we place it so that we apply the input to the system. And the input of this state space representation is U again. So therefore, it should calculate U based on x1 and x2, if it's a 2x2 system. If I have n of them, I'll have n signals, and I'm trying to come up with U. Now, here, it is important to note that I can use the matrix notation here. And if I have a scalar value on the left-hand side, if I have to need a certain thing, and I'm multiplying with a 2x1 vector, what could be the size of this thing here? Basically, it should have 2 here, because then I'm going to be able to multiply that. But it is going to end up in 1x1, so it should be a 1x2 vector. So what it really is I have the structure here. Let's call it the controller K. And this multiplication, if K is equal to K1 and K2, I'll have X1 and X2. This is basically the control structure that I'm going to use. And I can further expand this into K1 times X1 plus K2 times X2. And that's basically it. What I'm doing is I'm taking the state space variables, I'm taking the linear combination of them, K1 and K2 are the weights here, and I add them together, the linear combination, and that's my control signal. Now, up to this point, my control signal was basically K times E. That's the p-type controller that we are used to. But in this case, it's a bit different because we have a matrix structure. We have internal signals here called the states. And I can use each state individually, combine them, and apply it to the system. And as a matter of fact, if you remember the fact that we have defined x1 is equal to y, and x2 is basically x1 dot, which is y dot, you could also think of this controller as a feedback PD controller in some sort, because you have the output and the derivative of the output, and you're combining them. So it's kind of a structure like K1 times y plus K2 times y derivative, or I could call it K1 plus K2 times S, something like that. So it's a feedback PD controller in some sort, but it's not exactly the same because we don't have the error and its derivative. Instead, we have the output and its derivative. But does it really matter if we are analyzing step type inputs? Not really. But you get the idea here. It's not exactly, but it seems like one. So yeah, and if you remember the classical talks about the PD controller and the p-type controller, their differences, you'll see that we have more freedom in this case, because for the p-type controller, we're choosing just one gain. But here, for the state feedback controller, we're choosing multiple gains. In this case, 2. Now, remember that U equals Kx. And let me also leave this here. Now, if we have this equation, and if we plug in the controller here, because U is not independent anymore, it's not any input, it's depending on X, and there is a linear factor there. So it's basically K times X. U is equal to K times X. So again, we have a common factor here. It's kind of an autonomous system in this case, because U is not present anymore. It's not depending on input, so it's autonomous. Now, can you see the corresponding characteristic polynomial here? Because we have x dot equals something times x. If I wanted to get the corresponding transfer function, I could do that, because s times x would equal to this a plus bk times x. And then again, this would be si minus x, and I would take the inverse. But you'll see that it would be the following determinant that I should be interested in. if I want to calculate the characteristic polynomial. And you'll see that this would give you s squared times something, let's say a2 plus k2 times s plus a1 plus k1, something like this. You can also obtain this by thinking about the feedback PD controller. So you can see that choosing K1 and K2 independently, I can basically assign any pole combination that I want, which is a big difference because the P-type controller is just limited on its root locus. Without plotting a root locus, without using the path of the branches of the root locus, you're not able to assign those poles if they're not on that path, on that root locus plot. But here we have two variables for a second order polynomial, which means that I can choose K1 and K2 as I wish. So there's no limitation on the poles, which is the biggest advantage of state feedback and maybe also the state space model. You can assign what pole combination you want. So that's interesting. Now, it says that design a controller. Now, of course, it is a way of designing the state feedback controller, but a more classier and a way better method is the Ackermann Formula. And I'm going to show you the Ackermann Formula, which is basically the following. You have a bunch of zeros here. And at some point, you'll have 0, 1. And then times the inverse of a certain matrix, namely the controllability matrix, and then something called PDA. This is basically K equals that. I like to use a minus sign if I want to include it like U equals KX, or if you are using this Ackermann formula, you have to use U equals minus KX. So it's really a sign thing here. Now, if you have a second order equation or a second order model in this case, then you'll end up with this here. It is just going to be 0 and 1. And then you'll have a certain inverse and then PDA. Well, PD is actually PDS. So remember the polynomial that we were choosing for 10 weeks now? We are going to use the same polynomial here. But instead of using the polynomial itself, we'll plug in the A matrix here. It might be a little bit awkward, but it's really not. There's a theorem called Kylie Hamilton, if I'm spelling it correct, I'm not really sure. There's something like this. And it's basically proving that instead of using the SI minus A plus BK, if you are plugging it into the characteristic polynomial, if you have, that's for example, a certain pole, if you plug it into its own characteristic polynomial, you will get 0. So therefore, you don't really have to care about the whole thing. You just plug in the A part. The controller part can be omitted. So it's not really, again, our discussion. What you will do is you will just form something like this, maybe S squared plus 2 times zeta times omega n times S plus omega n squared, but you have to plug in S equals A. So that's important. And if you want to plug in S equals A, S is a scalar, A is a matrix, you have to plug in you have to use an identity matrix for the scalars. Then you're good to go. So yeah, when you have done that, you will get PDS and plug in S equals A. You have to use this. Well, you know what this is if you have chosen zeta and omega n. That's not really that difficult to choose. Then you have this special matrix, which is basically defined as this, which has no unknowns in it. And this is just a vector. So calculating the state feedback controller based on A, B, and a certain polynomial, desired polynomial, is fairly simple. The only problem here could be the fact that you have to take the inverse of phi c. And if it's, for example, a 3 by 3 matrix, it will be a bit harder. The Sn increases, this will become more difficult to do by hand. Other than that, if you have a computer, it's pretty easy. And there's also a command for that called Acker or place. where you just give A, B, and then the poles. As far as I remember, this is also A, B, and poles. So you can use these in order to just directly obtain the result here, but I'd highly recommend you to use this method in order to design a certain controller. So yeah, I'm going to show you the solution of A and B and then move on to T2 because A and B are concerned about the special system that we have here. But for T2, we'll obtain a nice state feedback controller. We are going to design that. So let me first show you that part. Here you can see the detailed steps of obtaining a transfer function from a state space model as C times Si minus A inverse times B plus D. That's basically it. You plug in each matrix into this equation here. Since this is Si, you get this structure here. And at some point, you will recognize some transfer function like fractions. And once you are done, you'll get this here. You can see that there's a pole zero cancellation and you end up in 2 divided by S, which is basically this integrator here. Now, if we use the state space model itself and plot it, what we can do that, by the way, then we end up in this here. Now you can see that the output is basically X1, but there's another mode, in this case that was 3.8 something. The pole was not stable in this case, and you can see that it tends to minus infinity. But it doesn't affect the output, therefore it's not really that important for us. Now, if we have a p-type controller for the same system, 2 divided by S, we can just look at this, and I've also stated that. But if we want to look at the controllability matrix, which I've also shown, we will use B, and A times B, we get 0. Rank of this is 1, or the determinant is 0, or it's singular. The rank can you help out in determining how many poles you can basically control or change the position of. But the determinant will tell you if it's controllable or not. Now, instead of using A, B, C as given in the system, like these values here, or matrices, we can come up with a pole zero cancellation after that we have 2 divided by S. You can just directly choose a model on your own. And let me comment on that. If we have Y divided by U equals 2 divided by S, we can directly see that S times Y is 2U. And if Y is equal to X1, let's say X1 is equal to Y, this would give us the Y derivative is 2U. Well, if we have such an equation, the only thing that we end up in is 2 times U. So if you put this into a matrix form, or in the, if you define A, B, C, and D, you'll see that X1 has no effect on this, so I can assume that this is 0 times X1 plus 2 times U. So therefore, A is 0 and B is equal to 2. Now, based on line 41, you can see Y is equal to X1, so therefore we have C equals 1, and there is no direct input here, there is no U. So this is basically one of the models that we can use here. But I can argue that I can also use it like that, or any other combination that has B times C equals 2, which shows us that there's no unique state space model for a given transfer function. You can have anything you want, even a 2x2 model here. This one here is also the same as this one or this one. So we can have infinitely many state space models that share the same transfer function. But there will be only one transfer function if they are the same. Okay, that's really important. So therefore, the multiplication of BC can be changed as you wish, and you'll get the same transfer function. So that's basically what I wanted to tell here. Now, you can see that if we use the controllability matrix with a newly defined state space model, we'll have just B, and B is not equal to 0, which means that we can affect the system, which is again important because because we have x dot equals ax plus bu. If b is equal to 0, we will end up in an autonomous system where even applying any input does not change the system's eigenvalue or pole. So controllability makes sense in the scalar and is easier to explain in this case. So we cannot change the eigenvalue here because we don't have any effect. But if b is other than 0, then the effect would be plus b times k. So choosing k would change the eigenvalue or the pole of the state space model. So yeah, I'd say let's have a break because this was too much of an introduction part, and then continue on the second part. So let's have a little break. So now, the first part was basically more of an introduction phase. So now we have a second order transfer function here, and we'll obtain the state space model of that. And then we will look for a state feedback controller design, and then we'll also talk about the observer part of this story, and then conclude our session of today. So now let me just guide you through the steps here for the given transfer function. So we have basically 6s plus 12, 6 times s plus 12, divided by s squared plus 2s plus 101. So if we state this as a differential equation, if we convert it into a differential equation, we'll see that there's a slight problem with this system. So let's first obtain that. So we'll have this here. Now, if I calculated what it would look like is the following. We'll get this equation here. So if I expand this, I'll get 0.2 times y derivative, and then 101 y. And here I'd get 6 times u derivative plus 12 times u. Now, if I'm defining x1 equals y, x2 or x1 derivative equals x2, which is y derivative, and then x2 derivative would be basically y, the second derivative of y. And that would be it. But if I use this equation here and plug in x2 derivative into y double derivative, x2 into this one, x1 into this one, I have a slight issue here, because you can see that our model would look like this. Let me also take this one here. So we have basically this here, and let's move them to the right-hand side. So that is another thing. We move this here. Now, this doesn't really fit x derivative equals ax plus bu, does it? So what now? Because in this case, I need to have u derivative, but I don't really have that, because once I have the state space model, I'm going to design u equals kx, and it's not really possible if I have u derivative here. So therefore, in order to analyze systems or convert transfer functions into the state space model, what I should really do is I should have an intermediate step. And in this step, I should get rid of the numerator here. Instead of using this numerator, I'm just going to use 1. here, and then convert that into the state space model, and then care about the numerator later on. So I'm not going to attack this system as a whole part. I'm just dividing it into its denominator and numerator. And you might see why I'm doing that, because we have u dot and u. We don't really want to mess with that. So instead of doing this, what I'm going to do is I'm going to get rid of this part here. So my first step would be to define another transfer function. And that would look like this. I'm just taking the denominator, and that's it. So that's basically my first step, not the whole transfer function. And you'll see why. Now here, if I, again, cross-multiply it, I'm getting x here, and then here we will have just u. And this just u is really important. You'll see we have x, and then this is x, and then this is again x, and then we have x here, basically. And once we've done that, we will end up in x dot equals ax plus bu. So if I'm going to state the A matrix, it seems like it is minus 101, comma minus 0.2. And the first line here is 0, 1, because the first equation is this one, the second one is this. And then if I'm defining B, it would be equal to 0 and then 1. And that's basically it for now. I don't have really the relation between the input and output. I have the relation between the input and the state variable, sort of. So what now? Because I have only AX and BU, but we don't really know what C and D is in this case. And it's also not the complete transfer function. So in this case, since I've defined this, and we have basically this here, you can see where I'm going with this, because, well, I know a certain part of this, namely this part here. It's basically times x divided by u. And since this is a static equation, or it can be a static equation, if I multiply with u, you'll get y equals 6s plus 12. And again, expand this into 12x and then 6sx. Now here, instead of having u derivative or stuff like that, I have basically x derivative, which is already one thing that I've defined here. And that's x2. So I can just use x2 here and x1 here. And that's basically it. And if I want to use the expression cx plus tu, if I'm going to define c and d, c would be equal to 12 and 6. Keep in mind that x1 comes first and x2 is the second part. And d is equal to 0 because there's no direct term here. So if I would have ended up in something like plus u, I would have just chosen d equals 1, but that's not the case for this. So you can see that I've converted the system into the state space form, but I didn't directly use the whole system. I've just used the denominator in order to work with a and b. And this makes sense because the determinant si minus a, and if you have a controller, even b minus u, and therefore kx, so therefore bk. So there are two versions to this. I'm just concerning or working with the denominator. Therefore, the denominator defines a and b and nothing else. So I don't really need the numerator there because it's not really constructed out of the numerator part. I can just choose the denominator, the characteristic polynomial, come up with a and b, and that would be one part of my model. And once I've done that, I can just directly compose any output out of this a and b. I have to just choose the right C and D matrices, and that's it, basically. So I can also show you the fact that if I have, for example, s squared plus 6s plus 12 divided by s squared plus 0.2s plus 101, this would work. And you can just see why. Because, first of all, my first step would be to use this. So I will have basically the same A and B matrices for this transfer function. But another additional step would be to use this here, s squared plus 6s plus 12. Now, if I have it here, so let me just use that. If it's like this, then I get something like this, s squared plus 6s, and then again here, and then that would be x double derivative, and then plus 6s x, etc., or s squared basically, and then x double derivative plus this. Well, at this point, it's not really that helpful. And I've told you about the fact that if you have a biproper system, then you will have D. So this extra term that causes me an issue is basically D term. I don't really have to use this form. I can just come up with a better version here. That would be 1 minus AS plus B. Let's call it that. So instead of using s squared plus 6s plus 12 divided by s squared plus 0.2s plus 101, I see that there's s squared here and s squared here. So I can just decompose it into 1 minus or 1 plus as plus b divided by s squared plus 0.2s plus 101. And here this 1 came up from s squared divided by s squared. So the highest term division gives me basically the direct path. So the d term will be 1. The only extra step that is needed is to basically write this down, s squared plus, so let me just copy this. So this minus as minus b should be equal to this term here. So you can see directly s squared goes or is canceled out. So yeah, if it's plus, it could be also plus. It's not really that important here. Change it. Here I can see what A should be, what B should be, and I can just use that for this step here, for the second part here. Instead of 12 and 6, there will be B and E. Therefore, I can just directly calculate it using this equation here. So therefore, if you have a certain transfer function, you can use this method in order to acquire the state space model. You can just look at the denominator, come up with A and B, and once you have done that, you can just look at the numerator. If there's a biproper transfer function, if you're using that, then you have to work out D first and then adapt the remaining parts in order to come up with the C matrix. And that's basically it. But in our case, we don't really have that. We have just 6 and 12. Let me just get rid of everything here. Yeah, this is A, B, and this would be C and D. So again, we can just check if we have this, if it's a valid thing. This should be basically the same transfer function. So there we go. You can see that here TF gives us basically a continuous time transfer function, which has exactly the same coefficients. So we have basically acquired a state space model here. And again, you can check for the eigenvalue of A, and you'll see that this is basically that. And you can just check the poles again. 1.2 and 101, and you can see they are the same. So the eigenvalues of A is basically the poles of the system. So that's it. You can also check if it's a controllable system, if it's an observable system. If the system is controllable and observable, we call it a minimum realization. Therefore, we have min-real. So you can just remember that fact, and you can see that if there are pole zero cancellations, they should be canceled out. Then you will get basically the minimum realization. If there's a cancellation, you will not have at least one of the things satisfied, namely the observability or controllability. So we have the system. If I want to, for example, design a certain controller to it, let's design a p-type controller. I'm not really choosing the poles here, which I'm just going to come up with a gain. Let's say the gain should be equal to 2 for some reason. Then I can just look for the closed loop transfer function, feedback, and that would be then k times gs. So do we have gs? I think not. Yeah, let's define it. Six, 12, done. There we go. Now that's the transfer function. Here we have the state space model. Here is the controller, and I'm just choosing a certain controller. And let's see what the resulting closed loop transfer function looks like. So that's our transfer function. And if I look at the poles and zeros, I can see that it's, for example, an overdamped system, which has a rough pole zero cancellation around the value 2 here. So it's basically kind of like 12 divided by s plus 9.6, something like that, roughly. So choosing the p-type controller, you have to use the root locus. What about the state feedback controller? In order to compare them, let's design a state feedback controller. So I have A, B, C, and D, and that's all I need. I can just come up with the controllability matrix. I've talked about that. So that's B, comma, A times B. And then I need basically a PDS. So for starters, I can just go ahead and use these poles to define basically the desired polynomial. So I didn't choose zeta and omega n just to illustrate you something here. I want to compare the p-type controller to the state feedback controller. So let's assume that this is the desired polynomial that I want to achieve here. So I have PDS. Now the interesting thing here is that I need the coefficients here, coefs of PDS, and I'm manually constructing PDA. And let's say coef 1 times A plus coef 2 times A plus coef 3 times the identity matrix. So by PDA, I mean this. So I take all the coefficients. I know that this is a second order polynomial. Therefore, there will be s square, s, and the constant term. I'm taking those coefficients. Instead of s square, I plug in a times a, which is a square basically. But I'm showing you that this is a matrix calculation. This is some scalar times a. And then we have the second coefficient, and then we have 1a because there's s, and then we have the constant term. But in order to be able to sum these terms up, I need to append this identity matrix because it's a scalar and we have matrices. So that's PDS, that's phi c. The only thing that's left is, let's call it state feedback. I'm going to use the minus sign here. We will have 0, 1 times the inverse of the controllability matrix times PDA. So KSF. It's called phi c, not phi. Of course, we need to convert it into double because we have used basically coefs here. in order to prevent that, what we can do is we can just go ahead and change this into double. There we go. Now, the p-type controller that we've chosen was basically equal to 2. It's a static gain 2. But our state feedback, since it uses 2 coefficients in this case, we have minus 23.9999 and minus 12. So I can just safely assume that this is minus 24 and this is minus 12. Yeah. So what about the closed loop? How does the closed loop look like? So let me show you the general closed loop of a state space model. Since I have kx in this case, ksf times x, I have a common factor, therefore I'll get this here. And the same goes for y equals cx plus du, because u is again ksf times x. And again, I have a common factor, which means that we'll have this here. So can you tell me what the transfer function of this model would be equal to? Because we have all the matrices that we need in line 23 and 24. How can I build the transfer function, the corresponding transfer function? Well, we have A, we have B equals 0, but I'm going to use the same B because what I can do is I can just do kx plus r or u, something like that. So let's call it that. In order to have a certain input here, that would end up in dr2 here. So let's call it r. Now I can build a state space system and I can convert that into a transfer function in order to observe the transfer function with the state feedback controller. So that would look like this. I can also use C times SI minus A inverse times B plus D, but let's be a bit more lazy. So there we go. Now, of course, I need the multiplications here, and that should be it. So if I run it, it gives me a closed loop here, and I want to convert it into a transfer function object. Let's also do that. There we go. Now we have TS. And we have TSF. Now, the only thing that is important here is that we have the same characteristic polynomial, s squared plus 12.2s plus 2501, and it's the same. But there's a slight difference. You can see that this is 6s plus 12. This is 12s plus 24. So there's a gain difference here. But other than that, it seems like it's the same. So let's look at ZPK of TS and TSF in order to observe the differences here. There we go. We can see that we have the corresponding poles. We have the same 0. There's a slight gain difference. But other than that, we have the same setup here. Interesting, because I've chosen the same set of poles for both of the designs. And I got almost the same with a gain difference that I can also basically fix, but it's not really the point of today. So yeah, I can use state feedback instead of p-type controller, or p-type controller instead of state feedback for this set of poles, but only for this set of poles. Now, remember our C matrix here. It was 12 and 6. And our state feedback gain was roughly 24 and 12. So it's almost twice the size here. And we've chosen k equal to 2. So it seems like if we use this set of poles, we are aligned with the C vector here. KSF is aligned with C. So that brings me to the following point. I'm basically using SF times X here, X, but I can approximate KSF with this because it's twice as large. Maybe a minus sign would also fit here, but that's not really important. And since D is equal to 0 and Cx plus Du is equal to Y, I'm basically feeding back the output here. And you can see why we have minus 2y, because ideally, U is equal to K times E. And E is equal to R minus Y. And if R is equal to 0, then we have K times minus Y, or minus Cx, or even for minus KCx, which is exactly the thing that's happening here. Exactly here. So why would I use a state feedback, or what is the advantage of the state feedback? Well, I've chosen the exact same poles, but for the p-type controller, I will show you the limitation. So since we have GS, what I can do is I can use the rootlookup command in order to see which poles are available to the p-type controller. So if we choose this set of poles here, so let's have that. If I choose anything on this, and I've chosen an overdamped one, and the gain was equal to 2, so basically gain is equal to 2, roughly here. I've chosen this point basically, and the corresponding point was somewhere here. It's not even on this plot, but yeah, you get the idea. So what if let's try something interesting. I might also choose this point here, but yeah, it's not really that important. Let's choose minus 6 plus and minus 1i. So what happens if I choose that? So minus 6 plus I and minus 6 minus I. So these will be my roots. So S plus 6 plus I times S plus 6 minus I. So I'm going to choose it here. So let me copy this. There we go. And I don't really have to change the code here. So let's see. Times here is missing. There we go. We end up in a certain K here. We have TSF. And if we look for ZPK TSF, well, the roots of the characteristic polynomial 1, 12, and 37, you see that they have exactly the values that we expected from. And we have a certain state feedback controller. But in this case, if we are using a p-type controller, it's not possible to use this set of poles because it's not on the root locus. But another interpretation would be the fact that it doesn't align with C. So if we have KSF, so let me write it down, and C, if I'm using a p-type controller, it seems like we have a 1/2 ratio here. And no gain with 1/2 ratio does satisfy the set of poles. If I'm using a p-type controller, I'm using a special version of the state feedback controller because they have a certain ratio because of the C matrix. But if I'm using state feedback, it's not feeding back only the output. It can combine the states as I wish. Therefore, it can assign the whole S domain on the left half plane if I'm trying to design a controller. But in order to be able to do that, I need to check the controllability. So if the system is controllable, then I can do that. If not, I'm not really that free anymore because I cannot affect that pole or that eigenvalue. So you don't really have to, by the way, use this transfer function, this closed loop transfer function. You can just check the eigenvalue of this. It's basically the same. You don't really have to calculate the transfer function here. So therefore, on this S domain, if I'm using a p-type controller, I have a specific x1 to x2 ratio. Therefore, I can only assign these values. If I'm using the state feedback controller, the whole left half plane is open to my choices. So that's nice to have. Or you can use a feedback PD controller, which is basically, again, the same because kx1 plus k2x2 is basically a PD feedback controller. So that's all about that. So let me talk about the observer here. Now, what is an observer and why would we need such a thing? Well, the limitation here is to measure x1 and x2 because my control signal is k times x or k1 times x1 plus k2 times x2. Now, assume that we are able to, or we have a controllable system. We have designed our controller and we know what K1 and K2 should be. The problem now is to implement this controller. And during the implementation, we have to measure X1 and also X2. Whereas in the classical control, we have to just measure the error, or we can just measure the output because we can construct the error ourselves like this. So let's call it KP. So this was our control strategy. Therefore, we need to only measure Y. But in this case, we have to measure X1 and X2. And this might be sometimes expensive, sometimes impossible. For example, if your model for some reason has magnetic flux in it, and measuring magnetic flux is not really that cheap or even possible, or you have to, for some reason, measure the rotor current, for example. Such applications need special structures because we don't want to really measure everything, or because there's noise, there's disturbance, we don't really want to do that. How can we avoid that? We still want to use state feedback, but we want to avoid measuring everything. We want to measure minimum stuff so that it is cheap and it works. Well, the observer is useful for that purpose. And the way of doing that is the following. If I know the differential equation of the system, I know how it's going to evolve throughout time. Because we are dealing with linear time invariant systems, it's not really that hard to come up with the way that the system will behave. And the mathematical model gives it away. We can exploit this model so that with minimum measurement, we can somehow reconstruct X1 and X2. That's really the point of the observer here. Assume that we have the given system here, AX plus BU. So let's say X dot equals AX plus BU. And therefore also Y is equal to CX plus DU. So I know that this is the system and I want to access X here. What I can do is I can do the following. I can just build a replica here, which has the exact same ABCD matrices, and I can run them both. So this is the actual system, an electric motor or something that I'm working on, but this would be the mathematical model. And if the representation is good enough, I can work with that. The only problem is the following. This is a set of differential equations. The model is built on that. So it might have initial conditions. So the initial conditions play an important role here because they will start evolving from that point. The model will start evolving from this point, from the initial condition. So I need to know that, but I can't really because, well, the system is replicated, but I'm not measuring the initial condition. That's not really possible. And if I'm measuring the initial condition, I'm still measuring x10 and x20. So this is basically two measurements which I want to avoid at this point. So what can I do? Well, the theory is the following. If I compare the outputs and somehow feed that back into my system, I can correct my replica system here, my observer system here. And I can do that by feeding back the output differences. So I'm just measuring output as it was in the classical sense. And I'm using my replica system in order to correct my system so that instead of using x and measuring x, I can use x dash, this replica x here. So that's the whole point. If I achieve that, if I choose L so that this system tends to this system, corrects itself, then I can use x dash, and that's good to go. Then I can use u equals k x dash, and I'm basically done. I'm again still using only the output, but I'm calculating all the other stuff out of it. So how can this be possible? Now, in order to prove that this might be possible, let's construct the difference between the actual model and my replica system here. And let's look at the derivative of the error because the error will evolve. So therefore, this is dynamic. So let's take this into consideration. Now, I know that x dot is equal to ax plus bu. So let's plug that in. And here, I have basically the right-hand side here. The whole thing here. There we go. Of course, everything has a minus here. I should have added this to here, not there. There we go. That's better. X plus bu, then minus this. So it makes more sense. Now, since we have, again, linear systems, since I know the model, this here is not actually that complicated. Now, I know that y equals cx plus du. I'm going to use that information. And I've constructed almost the same. So x dash minus du. Yeah, that's basically it. Now, we can see that du, so plus du, minus du, they cancel each other out. And again, bu and bu cancels out. Now, again, here we have x minus x dash and a common factor a, and then cx minus cx dash, again, a common factor c. So if we rearrange this a little bit, we'll see that we have basically a x minus x dash minus L, pull out C here, x minus x dash. So by definition, I've already shown or defined E as this difference. And on the right-hand side, I can see that it reappears. So let's change it to E, change it to E, and again, we have a common factor. So this is basically it. So this is really, really powerful and interesting because if we have a stable system, if x dot equals ax is my system and a is stable, then x will tend to 0. Because if you're just stabilizing a system, the energy will run out and the equilibrium point will be 0. Therefore, if A minus LC is stable, E will tend to 0. Just from this fact. Therefore, designing L such that A minus LC is stable will end up in E tending to 0 as time progresses, limit t to infinity. E will go to 0. Therefore, this difference will tend to 0. Therefore, my replica system states will tend to the system states. Now I have acquired the actual system states. Now I can feed that back. So it's really interesting. By coming up with such dynamics, I can just go ahead and design that. The only thing that I've used is basically a feedback of the difference between the outputs, and that's it. The difference between the outputs is really important. I feed that back. It's kind of a p-type control thing where I stabilize that, but it doesn't really control anything. It stabilizes the error dynamics, which then gives me basically the measurement that I'm after. So the observer measures that. And the mathematical kind of way of showing you that is the error dynamic given in line 45. Now this, choosing A minus LC, is actually nothing other than that. If we take the transpose here, we'll see something interesting pop up. This would be C transpose, L transpose. Now stabilizing this looks like stabilizing A minus BK. We know what A transpose is. We know what C transpose is. We have A and B. We don't know what L should be. We don't know what K should be. But we know that both should be stable and their eigenvalues should be stable. And we want to know what L or K should look like. So you can basically treat this as a state feedback problem. And that's the beauty of the thing. If you know how to design a state feedback controller, you know how to design an observer, because it is the same. But the only difference here is that I've chosen to take the transpose here. So you can treat a state feedback A as A transpose for the observer. Instead of using B, you can just use C transpose. And instead of designing K, you're basically designing L transpose. Therefore, using, for example, if we check the controllability matrix, something magical will happen again. Instead of B, I'm going to plug in C transpose. So it's transposed here. And instead of A, I plug in A transpose. Instead of B, again, I plug in C transpose. Now, what happens, and let me say that this is phi O basically, what happens if I take, again, another transpose here? A little bit linear algebra. But eventually, you'll see that this would be C, and then this would be C times A. And there we go. You have basically the observability matrix here. Therefore, my Ackermann formula for K, if I again inspect that, let's have 0, 1 times the inverse of phi C times PDA. Instead of using this, what I can do is I can just plug in L transpose, phi O, and again, PDA transpose. But PDA transpose is the same as PDA. It doesn't really change. Therefore, you can use this formula, or you can carry out this transpose here and use PDA times the inverse of phi O times this times 0, 1. So you can use this observer Ackermann formula, or if you don't really want to work with that and bother with that, just plug in A equals A transpose, B equals C transpose, and K equals L transpose, and use all the formulas, all the stuff that you've used up to this point. And once you've done that, you can just construct these two systems. You can use Simulink, you can drag and drop a certain system. For example, you can drag and drop the transfer function version of this, and then design the observer. Basically, what you need is this, and only this. Once you've designed the observer, you know what L is. Therefore, you can just construct your replica system here. And then you will end up in a observer that gives you basically X. But here we'll use X dash because that's the measured X, and you can feed that back into the system. Then you have an observer plus controller system, or more specifically, Lundberger observer with a state feedback controller. Then you would be happy to go. Now, let me quickly show you what it would look like. We've talked about this part here, so let me skip that part. I have also illustrated you how to design the p-type controller and compare it to the state feedback controller. Now here, we have a certain design, and this is basically the closed loop transfer function. This is the p-type controller, this is the state feedback controller, or vice versa, I'm not really sure. Here, the observer design, I've talked about this, you can check it out here, A minus BK, A minus LC. They are basically the same. Because we are talking about eigenvalues, you can transpose it, it doesn't really change. And then what do we have here? Well, here you can see how I did convert the Ackermann formula into the observer form, but it's not really that necessary. You can just plug in the transposes there. Now, if you use Ackermann formula, if you use A transpose, C transpose, and -3 and -3, for example, and take the transpose of the result, you'll get the Lundberger observer gain that you're after. Here you can see that I have the actual system. Here you can see that I have the replica system, and I have a error correction feedback here. And this is the whole dynamics of the system. And I have the Matlab code. You can just run it or use Simulink, and you'll see for a certain initial point, by the way. If you have initial point 0, you don't really need the Ackermann formula or the Lundberger observer because they are basically the same. But again, you do need actually that. If you have disturbance here somewhere, then it will affect it, and therefore you might still need the Lundberger observer. Now here I have used -10 and 10 as initial values for the states, and I have basically the observer, and you can see that at after a certain time, it basically tracks these states here. And that time is basically based on the poles, because these poles will define the speed of my observer. And here's an important thing about that. If you're designing a observer in conjunction with a state feedback controller, you have to be really careful because your observer should be way faster than your controller, because it is trying to achieve the correct state values here. And if your controller feeds back its signal based on false information, it will not work. So if you have a settling time for your controller, you should maybe choose a way faster settling time for your observer. So maybe 10 times, maybe 20 times faster would be a good thing, because, well, it is measuring or calculating the correct values, and it takes time. So you should be really aware of that. And that basically concludes our today's lesson. Well, we have looked at the state space model, and as final thoughts, what I can say is that the state feedback control is kind of a generalization of the p-type controller, but it has its dynamic parts because you're not really statically feeding back stuff, because x1 is maybe static, but x2 is not. And its derivative, it's certainly not. So therefore, you have an interesting pole assignment problem here. So you can assign any pole combination you want. And this is the most general version of that. If you have a second order system, you will have 2 gains, which is sufficient to assign all the poles on the left half plane. If you have a 5th order, for example, you will have 5 gains, which will correspond to each pole. Therefore, you can assign them freely. But it has a cost, and that cost is that you have to measure 5 different signals if you have a 5th order system and a state feedback controller. And if you don't really want to do that, you can just use the Lundberger observer. But still, it's not that cheap, because you will have the exact system replicated. This means that a 5th order system plus the 5th order replica will give you a 10th order overall closed loop system with a static controller. So we are aware of that. And other than that, we're using basically a matrix notation, which is the differential equation itself. For some systems, for more advanced applications, it's rather simple to come up with a model that includes the motion equations, and it will give you basically a linear state space model. And it is more detailed in terms of the internals of a system. In the classical sense, we designed controllers for two dominant poles, and then all the other poles were pushed away. But here in state feedback, that's not really the case. Here we look for disturbance rejection, noise attenuation, and stuff like that. Of course, not in the scope of this course, but generally. And then there are LQR and other controllers based on state feedback controller, which optimize the system in a certain sense. So it's a more advanced topic, therefore, and it's a more modern control strategy. It's important to talk about this in this course and conclude the course at this point in terms of the laboratory sessions. So that's basically it for this week. Next week, we will have our final session. Again, it will be on Monday. And if you look at the list that I've prepared for the homework 3 oral examination sessions, you'll see that there are the hours, but I will announce it back. So next week today, at this laboratory, I'll just announce it. We will have the final session next week. Other than that, that's basically it. See you next week in the final session. Evet, sorusu olan varsa bu arada cevaplayabilirim. İmza kağıdını getirirseniz bana sevinirim. Haftaya yine duyuru yapacağım. Burada yaparız muhtemelen. Finale hazırlık soruları çözeriz. İyi günler. Türkçe sınıfında geldim, tamam.
For the homework 3, will the late submission be opened again?
And since there are not that many groups and hopefully not that many late submissions, you can just directly mail me. But keep in mind that for each day, 15 points will add.
Okay, thanks.
Hocam çok fazla soru sordum.
Hiç sorun değil.
Bakmayın ama şimdi aklıma geldi o. Ben PID tasarladığımda işte ikinci soruda istemem.